Okay, I think we can start. So, welcome to the fifth session of the AI training. Uh, so, today we are going to continue discussing data issues. If you remember, the last time we were midway through discussion of various data issues that can rise, and so today we are going to start with the discussion of sampling. This is something that Dr. JK had brought up as a question in the last session as well. So it's a good way to segue into this session. So remember that we talked about the importance of having data that is clean, right? I mean, data cleaning being an important step in in the whole AI modeling process. Now, you can have situations where the data is good, it's clean, and yet there are problems. So here's one very common problem that arises, and this is a problem that we face in almost every project that we do. And that problem is that the training data for the AI to learn from is not representative of the on the ground situation, right? So, for example, the training data can miss or lack certain cohorts that are present in the deployment environment, in the on the ground situation, right? So, for example, if you're going to use the model on the general population, the AI model, suppose it could be that the training data simply does not have old people represented in it. It does not have specific locations represented. Your training data is collected, say, from all over India, but it misses out on a few important states. May not have enough women represented, so there could be gender biases. May not have enough low income groups, which would be disastrous for the kind of work we do, because most of the work we do caters to low income groups, etc. Now, in such a case, an AI model that is trained on this type of data, even if it's clean, even if the data is good, even if the data is in large quantities, the AI model will not work well for those specific cohorts, right? And that's because AI is, as I've repeated very often, AI is essentially dumb. It reflects what it sees in the training data. So if your training data does not contain these important cohorts, the model will probably not work well for those cohorts. Um, the other situation that can arise is that the cohorts are present, but they're present in very small numbers. So, in other words, uh, there's this problem called the minority class problem. So, suppose you are building um, a binary classification model. By now, I think everybody knows what is binary classification. Yes, when it's trying to predict one of two classes, right? So let's say one of the classes called the minority class is severely underrepresented in the data. So your total data set can be very large, but one of the classes is highly underrepresented. And then what will happen is that the AI model doesn't have enough samples from that class to learn the mapping, to learn this correlation, right? So an example could be that, let's say in a LFU solution, for example, we are trying to predict if patients will eventually go LFU. And I have a data set of, say, 500,000 patients. But among those 500,000 patients, there are very few that actually go LFU, right? So say 100 or 200. Then that means that the LFU class is, first of all, it's the minority class, and secondly, it's severely underrepresented in the data. And this can also cause problems for the AI model because it simply hasn't seen enough data in one of the classes of interest. Yeah. Um, a, a sort of more advanced manifestation of the same problem could be that different classes in the data are underrepresented in different cohorts. So, for example, you can have, let's say, you're trying to build a screening solution or a diagnostic solution, AI based screening or diagnostic solution for TB, right? and you have enough TB positive patients in your training data, you have enough TB negative patients, but you don't have balance in various cohorts of the data. So, for example, among migrant workers, maybe you have too few TB negative patients. Now, what will happen if that is the case? The AI model will tend to predict that workers are more TB positive than they actually are, because the AI model will reflect that bias that existed in the training data. Or you could have too few TB positive patients among women in your data set. And then the AI model may try to predict that women tend not to get TB, right? So it may try to predict negative results. It will have a prior bias in terms of trying to predict negative results for women, right? And so these situations, which are very difficult to deal with, will result in a model that makes biased predictions. And that's not what you want. Let me pause here for questions, if there are questions in this. Okay, so here is an example. Let's say we develop a cuff-based diagnostic test for TB using AI, like we're trying to do. We're actually trying to build a screening test. But let's say you were to build a diagnostic test. For the data that is used to train the AI, let's say all TB positive samples come from Agra and all TB negative samples come from Nasik. And the diagnostic test has good accuracy when you test it on a subset of this data. Is there a problem with this? This is the question. Does anybody know? Can anybody hazard a guess here?
Can you repeat? All the positive samples were from Agra and
Yeah, can you see the slide?
negative samples are from Nasik.
Yes.
Oh, okay.
And overall, it seems to have good accuracy.
But it is
Yes.
not representative. Positive samples.
What is likely to happen? Aditya, yes.
Yeah, so any future data points from Agra will be more likely to be positive, and Nasik will more likely be negative, even though that may not actually be the case.
Correct. So the AI will tend to, if the AI is confronted with a patient from Agra, it will tend to predict positive. And if the AI is confronted with a patient from Nasik, it will tend to predict negative. And this will cause problems. So as Anshika, I think what you're saying is that, sorry, I can't read the comments very well. So I just saw something as it popped up. You'll have to speak out instead of writing in the comments.
Also pretty much the same thing. I said that it might be that we've trained a location classifier.
That's right.
instead
That's right. So effectively, what you've done is you've trained a model that learns to predict the location of the patient rather than a model that learns to predict TB. Yeah. Are there any other questions?
So while we receive the data for AI ML model training,
Yeah.
we should be cognizant that the data that we are receiving should be representative of the population on which we are intending to use the AI ML model.
Well, you will not always get data that is representative of the population, but the data that you feed into the AI model, you have to make sure that that is balanced in some way. You also don't want it to be completely representative of the population. So I'll give you an example. We know that TB affects less than 0.5% of the population.
Mhm.
Now, if you get a data set that is representative of the population, let's say you get 100,000 patients data to build a diagnostic test for TB, AI-based diagnostic test. Then I don't know what the actual percent is, but 0.5% of 100,000 would be how much? Be 500, right? So in your 100,000 patient set, only 500 will have TB. Now that may not be enough for the AI to learn to discriminate TB from non-TB. So you need sufficiently many samples in all the classes of interest, right? And that brings me to my next slide. So the solution to this whole minority class issue is that you should collect, in fact, disproportionately large number of samples from the minority class, not representative, more than what is present in the real world for training the AI model. So this is very important. This is and this is in fact what we do when we create a screening solution for TB. Now, if you can't do this, there is a second option, which is that in software we oversample the minority class. Oversample means that we simply duplicate the samples that we have. So if we have 500 samples from the minority class, what we feed into the AI is say 500 plus 500 plus 500, where we just duplicate the data to make it look like there is more data so that the AI has more examples. And this doesn't work as well as actually collecting more samples from the minority class. Okay, please interrupt me if there's something you don't get here. Okay. Now, this oversampling process where you actually duplicate data that is present in the minority class may have to be done separately on different cohorts if there is a different minority class for each cohort. So let's separate these two things, the cohorts and the classes, right? The cohorts are sort of natural subpopulations. For example, you could have a gender-based cohort, males, females, right? You could have a location-based cohort, patients from different locations. And you could have within each of these cohorts, you could have different classes. Classes in the sense of depends on what you're trying to predict, right? So if you're trying to predict TB, you could have different proportions of TB positive and TB negative individuals in each cohort. Ideally, what you'd like is in every cohort that is of interest, in every cohort where you expect or you suspect that a bias could occur, you should have enough samples from both classes of interest. Right? And that's what I'm trying to say, where I say that the aim should be to achieve a balanced sample on every cohort that is of interest. So this is part of the work. So if AI scientist gets a whole bunch of data, part of his or her work is making sure that they resample the data in such a way that what is fed into the AI algorithm is a balanced sample for training. Okay, just to make sure that the AI has seen all types of positive patients, all types of negative patients across cohorts and enough diversity. This goes back to the data diversity issue. Yeah.
Doctor,
Now yes, Jake.
so I understand this inflation of the desired minority class just to
Yes,
make the
yes.
models more robust. So
Yes.
until what time this needs to happen? Only for the initial training part, or does it need to happen on a continuous basis? When I
No,
even
whenever you're training the model, you should ideally have good representations from all the classes that are of interest.
Mhm.
Whenever
So
you're training the model.
is there an objective desired proportion?
No, there's no. Well, objective desired is as close to 50-50. Let's say you
50.
have, yeah, let's say
Yeah,
you
I
have two
mean,
classes.
correct,
If you
correct.
have two classes, then you want to be as close to 50-50. If you have three classes, you should want to be as close to equal one third, one third, one third as possible.
Correct. The moment I try to do that, like, will I be compromising on my overall sampling universe or the overall N?
You may. So this is why. So there's two ways. That's why I didn't talk about downsampling. There's two ways to make it 50-50. Okay. So let's take a very concrete example. Say you have 100,000 data points in your training set.
Right.
Again, if going back to the diagnostic solution, it could be 100,000 patients, right? 100,000 individuals rather. And of those 100,000, only 500 have TB, and the remaining 9,500 don't have TB.
Right.
Okay. Now, there's two ways that you can ensure a 50-50 representation. One way is to simply take 500 from this 9,500 of negative individuals, and you create a total data set of 500 plus 500, which is
Correct.
1,000 patients, and feed that to the AI for training. The other way to do it is to just duplicate the 500, uh, say 19 times,
Okay.
to make it 9,500, and you couple that with the 9,500 negatives that you have. There are many other ways also to deal with this. I've sort of mentioning two simple ways. Out of these two ways, the latter way is better because then you're using all of the data and usually results in a better, more robust model.
Right. So I'm a bit surprised. I don't know the deeper layers of the LFU splitting, but in our LFU model, did we also
Yes,
have this, because
yes,
LFU represented only 5% of the.
yes, we did. We did this oversampling in a slightly different way. We actually implemented in what is called the loss function for training, but it's roughly equivalent to what I'm saying here.
Understood. I'm certainly aware that this has been done with the LPA with very concrete examples of
Yeah,
inflating the
yeah,
the
yeah. In
system.
LFU also, it's been done in a different way.
Understood.
Um,
So when are simulations applied, Dr. Alpan? Synthetic data simulations, they are not real data, right?
what do you mean synthetic data
Yeah.
simulations?
Like
Uh,
in LPA, Soma used a technique of generating artificial data by
yeah,
using
yeah. So
simulation.
I'm not talking about synthetic data. There are techniques called data augmentation where you create synthetic data in order to help the AI to learn, but I'm not discussing this yet. Maybe we can do that in a more advanced, uh, maybe part two of the training or something like that.
No problem, doctor. Thank you so
Yeah.
much.
Yeah.
I have a query, quite
Yes,
a
Malay.
theoretical one.
Yeah.
Suppose, let's say there are two countries, country one and two.
Yeah.
Country one has 5% as a proportion of LFU, and country two has 45 or 50%.
Yeah.
In both the places, we have collected the data, fed the model, and prepared it. So,
Yeah.
what do you think? In country one, where the prevalence was low or incidence was low,
Yeah.
we trained the model by different techniques by augmenting these LFU numbers.
Yeah.
तो prediction में कितना फर्क पड़ सकता है?
It depends. So I'll come to that in a minute. So that's what I was trying to say is this, right? So this is roughly what we do when we are training the AI model. But when you actually evaluate the AI model, since you are going to be using the AI model in the real world with real world prevalence, you should always evaluate on data that represents the proportions found in the real world. You don't change the proportions on the evaluation set. So whenever you calculate metrics, because you are actually going to use the model in the real world and you want the accuracies to reflect real world accuracies as much as possible. Right. So Malay, what I would say that as regards to the question that you asked, I would try different proportions. See, all you want is sufficient samples of data from both populations
Right.
and across both classes, both.
Hmm.
So typically what the AI scientist does is when you have sort of confusing situation like this, they treat this empirically.
Okay.
So they create different mixtures in the training data set.
Mhm.
Okay. But they have a fixed evaluation data set. So because you should always compare apples to apples, which means that for your evaluation, your test data should be exactly the same. And the test data should reflect the actual prevalence in the real world. What do you mean by actual prevalence? You mean both. Your test data population should reflect the population proportions in the two countries. So if one country has a much lower population than the other, that same ratio must be reflected in the test data. And then within each country, if one country has a different prevalence of TB than the other, that same ratio should also be reflected in the test data. So what the AI scientist will do is to create a test data set or sample a test data set accordingly, which reflects actual proportions in the real world. But then for the training data set, you can create different mixtures, do oversampling and so on, and then see what gives you the best accuracy on the test data set, what mixture. So it's an empirical exercise typically.
Fair enough. Thank you.
Yeah. So let's go back to the previous example. Let's say your Cuff AI is evaluated in a village where half the patients are TB positive. Is this a fair evaluation or not? Anybody?
Certainly no,
Certainly no. Why? Yes.
because I mean we are assuming that in the setting where the AIML model is going to be implemented would have totally different
Correct.
proportion of TB positive patients. So
Yes.
this
Yes.
test population is not representative of the
It's
actual
not
population,
representative of the actual. Correct.
which you
Correct.
mentioned I think few
Yeah.
minutes ago.
Exactly, exactly. So you are right that you shouldn't do this. But the answer is slightly more nuanced. So it depends on what metric you are using to evaluate. If the metric, and this is something that we'll come to later, if the criterion or metric of evaluation depends on the prevalence, then you are right, certainly not. But if the metric doesn't depend on the prevalence, then you could still do this. Okay. So, and we'll get to this. What are the kinds of metrics or criteria that depend on prevalence? What are the criteria that don't, and so on. Okay. We'll pause here. Any more questions?
Alpan, one question.
Yes, Adit.
In this same example, so let's say when you were saying that if we have these two cities, Agra and Nagpur, and one has more positive, one has more negative. But if
Yeah.
that was actually representative, if that data set that was used to train the model was actually representative of what the case is in these respective cities,
Yeah.
then
Yeah.
it won't be wrong.
Then it won't be wrong. Then it, yes. So if that were actually the case, that
Yeah.
all TB positive patients come from Agra and all TB negative patients come from Nagpur, then it wouldn't be wrong. Yes.
So like that, so location may actually be one of the features which determine whether or not you're likely to sort of get TB, for example.
Yeah. So if there is a true location bias in the data, a strong true location bias, and the AI inherits the same bias, then it should be fine to use that AI. Yeah.
Alpan, may I say that events where the prevalence is low pose as much difficult problems for AI when compared to events which have a higher prevalence?
Events where the prevalence is
Use cases rather.
yes. So low prevalence use cases do represent a problem, primarily because of this reason. You have to resort to some of these techniques. If the prevalence is too high, then it's really the same problem in an opposite way, because then the other class has low prevalence, right?
Okay.
And in fact, you can encounter unusual situations like what we are encountering right now in our CUF solution, which is that, we know, for example, in the population, TB prevalence is low. But it's easier for us to collect data from TB positive patients rather than TB negative individuals for ethical reasons.
Right.
So in the actual training for the AI, it's the negative data that has low prevalence,
Correct.
which is a very unusual situation. It's characteristic of healthcare problems.
Right. And higher prevalence events by default have a higher impact. Can I say that?
What do you mean? The event doesn't have so the AI. No, it.
Let me simplify and give a context to you. You are a fresh
Yeah.
data scientist, or you are a good program person, and you are offered two use cases to dive deeper.
Yeah.
Okay. Which one will be a smart pick?
Yeah.
At the time, one is the complexity and the ease and feasibility, and the other one is, okay, when it reaches the ground, what is the social good that happens? So how do you make a rational decision if you want to work on only one?
Correct. So you have to look at impact, right? Now, if something affects more of the population, like you're saying, higher prevalence, then assuming that the AI is equally accurate in both cases, then you're actually the AI is impacting more individuals in the case where the prevalence is higher. So naively, that is true. But you have to look at other factors as well, right? How bad is the health condition? I mean, the high prevalence health condition may not be as serious as the low prevalence health condition.
Correct.
I mean, there's classic case where you have the choice between treating heart disease, or let's not even say heart disease, say treating diabetes versus terminal cancer.
Right.
Terminal cancer may probably have much lower prevalence than diabetes, but which is higher impact? This is a difficult question to answer.
Right. Thank you.
Okay, let me go on. Yeah, just while we are on the topic of data and sampling, I thought I'd just briefly say a few words about big data, but this is entirely optional. This is something you just want to look at once and then not remember ever. That's fine. We're not really dealing with big data yet, but in the future, this may come up. So sometimes it happens, and this is a fairly technical issue within within AI and analytics, is that sometimes it happens that we have so much data that in order to analyze it, it doesn't even fit into computer memory for training the AI model, or even simply analyzing it, even running queries on the data. It's so big that it doesn't fit into memory. Now, if your data set is that big, that is called big data. And the problem that it won't fit into memory for you to even run simple queries like, filters, the kind of filters you run on Excel, or the kind of aggregation you do in Excel. If you're not able to do it, the data is so big that you simply can't do all of that. That's called the big data problem, right? And then the data set is called big data. And in such cases, there are various ways to train an AI model using big data. And this is often what is done in internet companies. Again, we haven't encountered this issue yet, but we may in some data sets in the future. So in such cases, we have, we have to downsample the data, which means you have to throw away some data in an intelligent way. So you downsample the data in a way that preserves its diversity when you're training the AI model. And you just downsample it, meaning select as little data so that the data fits in the memory, in computer memory. Okay? That's one solution to this problem. The second solution is some of the AI algorithms, most notably neural network as well as other algorithms. They can be trained in a distributed manner, where when I say distributed manner is where data is located on different processors, and the training happens across those processors in a distributed fashion. And that is also something that we would be doing eventually if we have to deal with really large data sets. So this is what we mean by big data.
So Alpan, I have a question on the previous point related to higher prevalence in a given geography.
Yes.
So if that's the case, isn't it possible that the features are not exhaustively defined?
What do you mean the features? Can you explain a little bit?
So, for example, let's say if there are two, or let's say country one and country two. So if country one has higher prevalence as compared to country two, and we have data available from both the countries to build some AI solution. And the feature list is such that it's common across both countries, and right, and then we say that since prevalence is higher in one of the countries, it may not be the right representative as a data set, right? So my question is that isn't it
no,
possible
why would we
country...
say that? Why would we say that? It is right representative for that country, right? I mean,
yes,
the question really is, where are you going to use the AI model? Are you going to use it in both countries?
Let's say, I mean, let me take an example of districts rather than countries. So let's say there are 100 districts. 2 districts have higher prevalence, very, very high, relatively high, like 50%, as you mentioned.
Yes.
Right. And in these 2 villages, there are some environmental conditions or policy situations which could be affecting those higher prevalence.
Okay, so if that is the case, then okay, I see what you're trying to say. So you're saying that if it could be that in these there's something unusual going on in these two districts that leads to high prevalence, and therefore the features themselves might have a different behavior or different distribution.
Yeah.
Yeah. So if that is the case, again, that can be exposed through data analysis of the features and so on. But if that is the case, it may be better in such cases to actually train two different AI models, one for the rest of the world and one for those two districts.
Okay. Yeah, that answers
Yeah.
my question.
And then use those AI models accordingly. That's sort of an extreme situation.
Okay.
There was another question on big data or something.
Yeah, Dr. Alpan, that was
Yeah.
me, JK.
Yeah. Yeah.
So when you're dealing with video files, so is the whole file consumed as one input data point, or will it be broken down into multiple frames and
The
convert?
way we are doing it in our projects currently is breaking it down into multiple frames,
Okay.
and we don't use all of the frames. It's often not very useful because the nearby frames are too similar to each other to yield uh, anything very different in terms of features.
Okay. I was just curious
So we
because
usually skip frames and have a sampling rate for the frames.
right in the Anthro model,
Yeah.
did we by default go with the more ambitious video sampling, or did we ever consider a photograph of the
We
baby in?
considered a photograph. In fact, that's the baseline model for
Okay,
Anthro, which is where you take a single picture and process that uh,
super.
instead of
And
a
my
video.
second question, Alpan, is you were talking about data characteristics when we are dealing with the actual data sets which have the labels, features, etc. Are there any desirable norms for contextual data to superimpose on the data?
So yeah, good question. So as far as the AI is concerned, the AI training is concerned, contextual data is not separate from other data. It's all one big data set, including all the features. In the work we do, contextual data often refers to data that is aggregated across individuals, right? So let's say we are trying to make a prediction for an individual, whether the person has cancer, whether the person has TB, etc. But one of the features that we use in that prediction has to do with where that individual lives. So say you're using one feature as the average income in that area could be a feature, or the average temperature in that location could be a feature. Now, this is what we tend to call contextual data, right?
Correct. Yeah,
But as far as the AI concerned, it doesn't care. It's just another column in the data set.
right.
Does that answer your question?
Yeah, it does. My question here is when we're doing labels and these things, we end up with the granular information like patient wise. Okay, what is the feature? But often at when I'm looking at the level of contextual data, I
Yeah,
get it at the macro level. So how do
yeah.
I superimpose it at a
You
patient level?
just you just assume that that macro level feature applies to every patient from that place,
Understood. Okay, okay.
right? So you just say if temperature, let's say you have a bunch of patients from I don't know, Bombay, and the temperature in Bombay is something. Say average temperature is a feature that you're using. Suppose average temperature is 31 centigrade. Then you assume for all patients in the training data set from Bombay, that value will be 31.
Understood, Alpan. Thank you.
Okay, so now we get into this question of generalization and overfitting. And in some sense, the whole concept of generalization is what we mean by the quote unquote by the magic of AI, right? So we know that an AI model is trained to learn a correlation between the features and the label, right? So you would expect it to perform well, meaning predict the label accurately on the training data, since that is the data it has learned from, right? So that's expected that the model will do well. But usually the way the model is used, it's used on data that it has not seen before. I mean, that's the whole point of capturing the correlation, because it should be usable on data that it has not seen before. Only then is it useful. So the ability of a model to perform well on unseen data is called the generalization ability of the model. It can generalize from the examples that it has learned from to examples that it has not seen before. Right? Meaning that correlation is preserved across from the training data to examples that is not seen before. And if the AI model can generalize well, meaning predict at high accuracy on unseen data, that's called the generalization ability. Yeah. Typically, if you look at, let's say, what happens is when you train an AI model on a set of training data. Now, if you actually compute its accuracy on that training data itself, it tends to be very high because it has learned the correlation from that data. But if you compute its accuracy on a test set, the accuracy will be lower always than the accuracy on the training data. So there's a dip. If the dip is not too much, if it performs comparably well on a test set as it does on the training data, then we say that the model has high generalization ability. Right? On the other hand, if a model performs well on the training data, but it doesn't perform well on unseen or test data, we say that the model is overfitted to the training data. So you will often hear this term when you talk with AI folks, that this model is overfit. And overfit generally means that it's doing very well on the training data. It's not necessarily doing well on the test data, and it really should be doing well on the test data. And one of the problems with complex models like neural network models is that they have a tendency to overfit. There are some exceptions, but generally the tendency is that if your AI model has too many parameters, it will tend to overfit and do very well on the training data, but not do well on the test data. On the other hand, if a model doesn't perform well even on the training data, so it's not performed well either on training or test, we say it is underfitted. Right? And underfitting is a hallmark of very simple models. Like linear models tend to underfit sometimes. If you have a simple model that simply predicts the same value of the label for everything, that's a model that will underfit. It will not even do well on the training data. Okay. And if a model doesn't perform well on training data, but somehow performs well on the test data, that's just luck. It doesn't happen. It can happen by coincidence, but usually doesn't happen. Eventually, our goal is that the model, or rather the goal of an AI scientist is that an AI model will perform well on test data, because that's data it's really not seen before. So that is the acid test of an AI model. That's why also people often say that, it's only in deployment that you know whether a model is working well, because the data that the model sees during deployment is data that's really never seen before when it was trained, or even when it was internally tested in the lab, and so on. Okay, so very important to understand this concept of, overfitting versus generalization. So there's a little cartoon here where we have three types of models. So the red curves in each of those represent the model, and then the circles and the crosses are the two classes of data points. So this is a binary, say it's a binary classification model that learns to separate the circles from the crosses. And the circles and crosses that you see are your training data. Okay, so let's actually start from the right. So you've got a model where you have a very complicated red curve that goes all over the place, but it separates the circles from the crosses beautifully. Right? All the circles are on one side of the curve, and all the crosses are on the other side of the curve. So this means that this model has 100% accuracy on the training data. But the model is so complicated because of all those curves and the way it curves back and so on, that it will probably not do that well on test data. And this is the kind of model that we say is overfitting. Then if you go to the model in the middle, which is sort of a simple red curve, which doesn't have perfect accuracy on the training data. You see there are two crosses on one side. And so some of the training data is misclassified by this model. Right? Is that clear what I'm trying to say here? But this model is probably an appropriate fit because it's not a very complicated model. It doesn't have, the shape of that curve is not very complicated. And on the left-hand side, you have a very simple model, which is just a straight line, which neither does very well on the training data, nor is it expected to do well on test data. And that's a classic case of underfitting. What
Dr.
a sweet spot is really the middle one. That's the kind of model an AI scientist wants to get at the end of the day. Yes, questions?
Dr. Alpan, from an earlier slide, I got a reflection that in order to comment about underfitting and overfitting, we need two prerequisites. One is the performance in the training dataset, and one is the performance
On
in
the test set. So
test
I haven't showed you what the performance here is on the test set. I've only showed you training set. All I'm saying is that, yes, you're right. All I'm saying is here, it's unlikely that the curve on the right will do well on the test set, just because that separation boundary between the two classes is so complicated that if you just slightly change the distribution of circles and crosses, if the test set has a slightly different distribution of circles and crosses, this model is going to do badly, right?
Right.
On the other hand, if you slightly change the way the circles and crosses are distributed, the middle one and the left one will do relatively similar in terms of accuracy. But the problem with the left one is that it has low accuracy no matter what you do, right? Whereas the one in the middle has good accuracy on training, not perfect, and probably will have good accuracy on the test set as well.
Alpan, what
Yes.
happens if I flip the class of interest? Will the same model be appropriate even in that class?
What do you mean skip?
Example, for this particular experiment, I am more interested in the circles, and
Yes.
I picked up an appropriate fit model. Okay,
Correct.
suddenly,
Very
for
good
some
question.
reason, the stakeholder is interested in the other class, the
Yeah.
crosses. Will
Yeah.
the same model be a good fit, or do I need to redo the whole thing?
No, you have to redo, because then what you're doing is, I'll come to this later. What you're doing is you're changing the criterion for accuracy or the metric. The accuracy criterion is what we call the metric. So you're
Right.
changing the metric of interest. If you're changing the metric of interest, you have to retrain the whole model. And if you retrain, you may come up with a different curve.
Understood. Thanks, Alpan.
Sure. Any other questions? If you don't understand something, if things are going above your head, please interrupt me.
Alpan,
I may just be going too fast, and I don't want to go too fast. It's not my intention. Yes.
Alpan, with regard to the appropriate fit, why am I getting a contradicting feeling that it's not the area under the curve, rather it's the area above the curve? Like,
It's not area at all. There's no area being discussed here. I have not talked about area, under, over, right, left, nothing. All I'm saying is that if you think of the curve as a boundary that separates the crosses from the circles, right? It's a classification model. So it's a boundary that separates crosses and circles. Look at the one on the right. Let's start on let me go through this again. Let's start with the figure on the right. Your red curve is a boundary that separates crosses and circles. You can see that the separation is perfect. Everything on the left of the red curve. So you should think of left as being one side of the red curve is a cross, and everything on the other side of the red curve is a circle, right?
correct.
So it's separating the two classes, the crosses and the circles, perfectly. So the one on the right has 100% accuracy on this training set. It's not misclassifying anything, right?
Correct.
Does everyone understand that? On the other hand, the one in the middle has misclassified two crosses because it's put them on the other side of the boundary. Just because of the shape of that curve, there's nothing else it can do. So it doesn't have perfect accuracy, but it has good accuracy. I mean, most of the crosses are on the left and all of the circles are on the right, meaning one side of the curve. Whereas if you look at the red curve on the left graph, which is really a straight line, both crosses and circles are misclassified. You should think of the red curve as being a a boundary between the two classes, or a separating membrane between the two classes. That's what the AI model learns. Am I clear or no? Yes, because
Yeah. So Alpan, I was just thinking, is overfitting a clue to figure out if we need more than one models?
no, not necessarily. There may be a number of reasons for overfitting. It could be that you have trained the AI algorithm for too long. It could be that the AI model has too many parameters. So in this case of overfitting, this example that you see here, the problem is that the model, sorry, yeah, the problem is that the model has too many parameters, because you need a lot of parameters to describe a curve like this mathematically.
Okay. And what do you do if you end up with an overfitted model?
So that's the thing that you do. So either you train it for a shorter span, shorter computer time, meaning you reduce the amount of processing, or you reduce the number of parameters. You set some parameters to 0 in the model to begin with.
Okay.
So there are various techniques like that to deal with overfitting. But usually the hallmark of overfitting is a big difference in accuracy between the same model applied to the training set and applied to the test set.
Okay. And will it be still valid if your data set is very large? You have all the optimal
Yeah.
conditions for a good training,
Yeah.
and you still end up with an overfitted
Yeah,
model.
yes, you can. That's why this is such an empirical science. There are no rules really. There are no rules that you can write down generally that this is what you should do. This is why experience is important. This is why so you really have to go through a lot of iterations to come up with a good model. You have to try a lot of different things. And part of my reason for doing this is for you guys to appreciate what the AIML people are doing when they're training a model. So they, often the first model that you build will be highly overfitted, or it will be highly underfitted. Something like that will happen. Then they have to play around with parameters. They have to tinker around, change a few things here and there till they get a model that is satisfactory.
Okay. And in this same graph, if let's say with crosses and circles, you also have a triangle.
Yeah, so you have
for
three
which
classes. Yeah,
3 classes, and the model has not been trained for the triangle,
right. Then it
right?
really can't do anything. Yeah. Then there's no
So
guarantees in how well it will do on the triangles. Yeah.
okay,
It may be do well just by coincidence, but that's not good enough.
okay. So, but if the triangle is getting classified into one of those classes, will you see that as an overfit, or I mean, is it an error? How do you see that?
So first of all, if you don't have a triangle class when the AI model is being trained, then it is impossible for the model to predict anything to be of that class, because it simply doesn't know. It's like saying that if you have a model that is only recognized uh, to count, to say, tell if a person is a man or a woman based on their photograph, right? and then you present it with a picture of a Martian and expect the model to say Martian, it's not going to be able to do that because it simply doesn't know what is Martian. It will call that photograph either a man or a woman, depending on what features it picks out.
Okay, that answers my question. Thank you.
Yeah. So, so the principle behind this is often called Occam's principle. This is after, I think, some English priest who lived in the village of Occam, but somehow the principle was named after the village. And the principle is that you should choose the simplest model that is compatible with the data, not simpler than that, and not more complex than that. And this is what we mean by an appropriate fit. In fact, and Einstein, in fact, said the same thing somewhat differently when he said everything should be made as simple as possible, but not simpler. Right? And this is really what we're trying to do with AI models. We're trying to find the simplest possible model that that gives you high accuracy on your test data. Okay. So we'll pause here for a little recap before we go on. And this is recap of both today's, some of the material that we saw today, as well as material that we saw last time. So or a very broad level, two types of things that AI does, two types of work. We saw this last time is automation versus pattern discovery. So AI models either automate a task that humans can already do and do it at high accuracy, or they discover a hidden pattern so as to carry out a task that humans can't do. And when AI does that, often the accuracy is not so high. But then you don't need very high accuracy because humans can't do it anyway. So even an AI model with medium accuracy is good enough. But these are the two broad classes of things AI does: automation versus pattern discovery. We looked at baseline models, which are simple models that can help us to decide if an AI solution is worth it. Right? AI solution is only worth it if it can do significantly better than a baseline model. If your baseline model is anyway has 98% accuracy, 99% accuracy, probably you don't want AI. Right? We looked at the whole data pre-processing pipeline, which consists of sampling the data, cleaning the data, annotating the data, and carrying out appropriate mathematical transformations on the data in order to create a final data set of features and labels that is then fed to the AI algorithm as training data. Okay? The training data is typically split into three parts: a training set, a validation set, and a test set in order to create the AI model. And this split is internal to the AI team and it's necessary for experimentation. Again, as I've explained, the validation set is a set of data on which you optimize certain hyperparameters in the model. Again, not very important for you to understand. And a test set is a set that is used for internal evaluation of the model. We talked about data quality as being essential to creating good AI models. And as a general thumb rule, we can't always achieve this, but as a general thumb rule, quality is more important than quantity. And the less accurate the data is, so the lower the quality, the more data you need, the more data the AI needs. So often AI scientists are puzzled when you ask them how much data, and the answer you'll get back is depends, and I know that's very frustrating for many people when you get an answer that says depends. But really what they mean is it depends on the quality, depends on what our initial experiments will yield in terms of accuracies and so on. We talked about data being diverse and representative, which is also essential. So there are all of these data issues, right? The training data should reflect the diversity and variations of the deployment environment, just as a central message. We talked about how much data is needed Deep learning models are more data hungry than classical machine learning models, but they are also much more accurate in a number of situations. So that's the trade-off. And then finally, we talked about AI respecting the Occam's razor principle, which is to choose the simplest possible model that is compatible with the data. So before we go on, let me again pause. I know there's a lot of new concepts here, a lot of things sort of whirring in your head probably. So let's just pause for a little bit to see if there's any reactions or questions. Yes, Aditya.
Yeah. So Alpan, on that question that you mentioned that, when it's asked to the AML team that how much data is required or what data is required, when we're
Yeah.
at the problem formulation in very early
Yes.
stages,
Yes.
even though the simple and the correct answer, as I understand, would be that the more the better, and we don't know. But what would
Yeah.
be a good way to think about it when we're early on in the problem, where we're trying to figure out what problem we want to solve,
Yeah.
and what data is available. So I mean, the
Yeah.
simple
Yeah.
answer is whatever data is there, you collect it. But is there
Yeah,
a
yeah,
more
but that's
nuanced
often
way?
not feasible. Yeah. So the nuance. So yeah, this is it's a very good question, and it's very important for all of us to understand, especially given how empirical this field is, right? So on the one hand, we know the correct answer is we don't know, but that's not an answer we can give to external stakeholders in many situations, right? Um, and this is where I think a number of things help. One is if we've solved similar problems before, then we can extrapolate and say, okay, when I solved a problem like this, and this is usually what people do in other places. See, most other places, unlike us, actually solve very similar types of AI problems as they move forward in time. Right? Then they don't solve sort of radically different problems. Whereas we are a very unique institute in the sense that we move from one class of problems to a radically different class of problems. And we at least so far haven't had the experience to be able to extrapolate from our previous work. Now, if you look at risk prediction problems, we've tried, LFU is a risk prediction problem. For example, pregnancy risk stratification is a risk prediction problem. We can take our LFU work and extrapolate from there to pregnancy risk stratification and say, okay, we'll need a few thousand rows in each class of interest, right? There is standard work in image processing that we can go to where we know that, if you want to train a deep learning model from scratch to just classify images into various categories, then you need 4,000 images in each class of interest. Right? For our video work like Anthro and so on, we really have nothing to go, fall back to in terms of data requirements. So we'll have to wait to gain that experience. But what I'm saying is, once we span a large enough space of problems where we have experience in terms of how much data we needed for various types of problems. And then we go on to the next phase where, we'll be able to map many of the new problems to problems we've already done and say, look, this is similar enough to that, and this is the amount of data I needed. I'm going to add maybe, just for safety, increase the requirement slightly over that and quote a number. But this is really what it is. It's not more sophisticated than that. And as we gain experience, this will get better.
Alpan, hi, this is Shekhar. Just a quick comment. Aditya, one
Yeah.
thing that we should do is we should create a matrix, an X by Y matrix, where X is a nuanced class of problems, a little bit proper, so that we create a conceptual framework with all the problems. Now we have 8, 10, 12. At some point, we may have 20 problems. And some of them will cluster somewhat similarly, but they will also have differences. So that's on the one axis. And on the other axis can be the quantum of data in a qualified manner. So we say that if you're doing a classification, you need, say, I'm making up just some number, 5,000, 25,000, 100,000. And the intersection should contain what are the characteristics and what is the way we believe at this stage we can solve a problem in that space. It's a classification problem. So if it's 5,000 in an image, that means very high quality images caught in this manner, done in this way,
Yeah.
and done. So we just kind of bound at this time in an open-ended manner with a big caveat below saying that, this is just a conceptual framework. This is not a prescription, an immediate prescription, but it offers a guideline. So that guideline, I think, is useful for us as an institute to start formulating and creating so that we have a reference chart that we can go to at any point in time. Maybe it's created once every 3 months or 6 months or whatever. And that becomes your guideline, because for the individual practitioners, maybe it's a little easier just referring to something and at least telling people what it is. That's all, Alpan.
Yes, agree. Yes. Vijay? Sorry,
I had
Aditya, you have a
same-
follow-up?
Yeah, I had the same question as Aditya actually, but I feel like we have this conversation across the board in the life cycle of the project. So
Yeah.
how to have those conversations to arrive at some basis for what additional data you need, so that you have something that you can take back to the customer.
Yes, it's difficult. At this point, it is difficult to sort of pin down with a number. And what will typically happen is we will generally see that accuracy improves as you get more data. And we will end up collecting the amount of data that is feasible to collect. And therefore, we'll also have to make that trade-off on the accuracy side of things.
Vijay, the other thing that you should do, depending on any solution, is I think try and think through at a concept level, and then drive to the number. So, for instance, if you have a multi-state data collection on something, or a multi-output, suppose one of the things AML will always ask for is there enough representation in each of these outcomes in terms of the data that you actually want to derive those outcomes. So if you want to come up with A, B, C, D, or colors blue, green, red, yellow, you really want the sample data to have enough representation in each of these. This is a thematic. So we can discuss the thematics, which will allow the dialogue to take place in a certain manner. So you can at least start telling them that, look, typically you'll need, and for a fact, and fairly quickly, we should come up with some basic guidelines. So you need for data. So we really need to drill down for data-oriented problem, for text-oriented problem, for this, for that. What is a quantum? And also, it also depends on the ease with which you can collect the data. But we really need to come up with a thought process. I would suggest that, taking a derivation out of what Alpan is teaching us, let's put our heads together and play act a few questions and come out with a few answers from our side, the solutions and the analysts, and let's just put those answers. It may be wrong. Then we'll get it reviewed with Alpan saying, is this thought process correct?
Okay.
But let's take a shot at it just as a consensus, as a team, just starting to think through kya answer देंगे इसका. Structured answer होना चाहिए, and because it's not that easy, but really we do need those answers at some point.
True.
I think Aditya has raised his hand.
Yes,
or is it
Aditya.
not?
Yes.
Yeah. So just one follow-up question, and I don't know if this question is correct, but with certain types of models, let's say models that come from data that have that use tabular data, so let's say predictive models.
Yeah.
Is there some during the modeling process? Is there some indication that we can get as to what other kinds of data could potentially improve the model,
Yeah.
or is that only let's say in our world a program input that can come in?
Yes, that's a good question. It's actually a combination of the two. So, so first is the plausibility. See, one thing to understand is if there is no signal in the data for the outcome, right? So, if this goes back to sort of piracy and global warming. If all your features are about piracy and number of pirates on ships and where these ships have been sailing and what is the material that went into the building of the ships, and your outcome label is the temperature of the earth, there's no real association between the two, right? Then no matter how much data you may give me data on 1 million ships and 1 million temperature points for the earth, all these correlations will be simply spurious, right? And so there's no signal in the data, and therefore having more data will not help. So the first thing to establish is if there's enough signal in the data, right? Which there are AI techniques to do some of that. Now, once you've established that there is signal in the data, that your features are actually predictive of the label, then we come to your question, which is, can we establish the number of the amount of data that is required and so on. Again, there we can look to past experience, but there are nuances there again. So, for example, remember I told you that the dirtier the data, the more you will need. So then the question that arises, the AIML team might see that, oh, this data is not very clean, and so we need more data of this type in order to build a good model. The other thing that can happen is, even if the data is clean, the signal may be very weak. So then the AIML team might go back to program folks and say, maybe there's an important predictor of this outcome that we're simply just missing in the data, and program will have to look at it. So this is something in our LFU case we've looked at. I mean, the whole need for contextual data came about like that there is data in Nikshay, and then there is data outside of Nikshay that could actually be very important in terms of predicting outcomes, right? Like population density of the region where the person is, various census type indicators, weather indicators, whether is a clear correlate, has correlation, weather, humidity, and so on has correlation with TB, and that's not spurious. But that data is not in Nikshay. So this is informed from domain expertise, and partly also because the AI team finds it difficult to predict beyond a certain accuracy, no matter how much data they throw at the problem. And that's when you know that you probably need some other features outside of the ones that you've already looked at. But typically the AI team will not be able to tell what are those features. That is something that will have to come from domain expertise.
Okay, thank you.
And Aditya, just and everybody, just as an example, just recount a conversation earlier today that is just seeded. So it's like day zero of this problem. We just had a casual conversation, Vikram and I. Vikram says agriculture has 11 crore farmers' data, and they're going to shortly announce that the Prime Minister, using some program, will be distributing 2,000 rupees to these people. So the question asked is, several of them may be fraudulent or may not be deserving the money, because as I understand, there may be some very affluent people who may own farmlands, and because they own the farmland of sorts, they get the money. So now the question that is asked is, can you detect it? And so here, now you come to two areas. One is, how do you label it? For a moment, let's leave that aside. Let's assume we have a small Chinese army ground force that, independent of everything else, is able to go down and validate that a farmer F1, F46, F48 deserves the money or not. For a minute, let's assume that is a solved problem. It's a difficult area, but let's assume it's a solved problem. Now the question that we have to ask ourselves, to Alpan's point, is, what is the type of data we need? What are the signal content of the data? So, government will say, nahi, uska naam hai. We know he's from here. We know he's from there. We may have some base data. Then our analysis needs to start. We should then start thinking of the feature set. We may need to look at demographics, census data, land, arability, images. We need to construct a complete long set of information points that then can be used as the pieces of feature information that can come to that conclusion. Then it comes how much data, what it is. But the reason I'm mentioning this as an example is because this is the first and the most important. I'm not a domain expert, but anybody who's working in a space who's presented with a problem like this should start thinking about the problem like I'm suggesting. One is the labeling, how to do it, what to do, etc. And ideally, the labeling must be divorced from the features. In other words, you must independently assess it. Does a person have fever? Shouldn't come from the data features. It should come from a thermometer measurement. That we understand. Then the features itself, you really have the analytical ability and very practically think of it. Not in some high funda, which will take 3.5 years to get to a data set. This is the most important first set of analysis that then, if you do this analysis and then give it to an AIML person, and then you can source the data in some manner. These are all very simplistic assumptions I'm making. Then the AIML team can look at the data quality very quickly, completeness, all the things Alpan speaks about, come back quickly and say, you know what, this is the amount of data we need. So this analytical thinking process is super important. You cannot not do it. You have to arrive as program people and domain people at a basic set of features that you believe is enough, commonsensically, for you to come to a conclusion. And that's the dialogue you'll have with the AML people. Does this make sense, Alban?
Yes, totally. So in fact, I would give you another example from work that we are doing right now, which is on the multi-signal model for cotton, where, what are we really doing there? Based on satellite information, soil information, and so on, we are trying to predict what would be the number of insects on a trap if you had put that trap on the farm. Now, this, no matter how much data you get, I don't see that we'll be able to go beyond a certain accuracy in predicting this, because there isn't enough predictive value in the features. What may be much easier to predict is, will the infestation exceed a certain level? Unfortunately, we don't have enough ground truth data for that, which is why we are doing the former problem. But this is an example of a problem that we are actively working on, where, we think you may need some additional things in order to predict the outcome of interest or simplify the outcome of interest.
And what Alpan mentioned is super important. It goes down to problem definition clarity. Because if the problem is overreached, if you overreach on the problem definition, in some sense, you will never be able to solve it. And it's a very frustrating experience. So the formulation of the problem must take into account the quality and the assurance of the labeling mechanism. The nature of the labeling mechanism should conform to the type of outcome that you are wanting to come to. And the types of data that you get need to be somewhat reasonable in order to come to these conclusions. This is the difficult part. The more research oriented or the more far reaching the problem is, the more difficult it is. This is a completely different problem compared to what we face in Anthro. Anthro's problem is a depth oriented, difficult problem, very constrained, but you have the image. That's all you have. Or a video, sorry, you have a video, 10-second video, 300 images. That's it, you have it. There is no more to be spoken about in terms of data collection on that. Quality, quality, all that is good. But there is no context of anything else. So you must recognize the type of difference typically in an image or a sound oriented problem in which the feature set is fully confined in that particular thing itself versus a data oriented problem, what Alpan mentioned, where you go into, weather data XYZ, or the one I mentioned where you go to farmer data XYZ, or LFU, where you go to ABC XYZ. There it's an unbounded problem. Unbounded means the feature set you will have to keep approaching in order for you to reach a feature set that you feel will be enough to solve a problem. That's a different class of problem. Whereas an image is a very simple problem. I'm not simplifying the solution of the problem. I'm saying the problem is very simple because all you get is an image. You have nothing else to go by. So this is a bound problem. Somebody coughs, it's a bound problem. You don't want pitch and noise, sound and all that is understood, but it's a bound problem. Understand the difference and the nuances between these two types of problems. Does it make sense, Alpan, to think like this?
Yes, except that sometimes we do augment. For example, in cough, we also have some symptom data and so on to make to improve the accuracy of the prediction. So we can augment like that, but within its defining characteristic, like a cough sound is a cough sound. There's nothing else that goes into it. And similarly with image.
Alpan mentioned a very important point. The performance or the accuracy or the performance of the cough on its own, let's say it's about 70-75%. But when it's combined with this other data, goes up to maybe 80-85% and may even touch 90%. So that's also an interesting. So there is always, not just one type of data, not just cough, sound, or image. You
Yeah.
may add other pieces of data, but I want people to start really thinking about these things. The way you think about these problems.
Yeah.
That's the change we need everybody to start, kind of feeling comfortable.
Yes, Aditya.
So, Shekhar, based on what you said, two thoughts came to my head. One is that then should we do what Alpan was earlier suggesting, which is what most AI organizations do, is focus on few classes of problems versus others, because they may be bound or we have experience, so on and so forth. And if so, or rather, second thing that came to my head is that within certain domains, is there merit in, let's say, a completely very simplistic idea, that we try to map out whether or not we're solving any problem or not, all the available public data sources in that particular domain that may have relevance to a broad problem set. So a broad problem set is, let's say, maternal mortality or infant mortality, or people getting affected by TB. So if whether or not you're working on it,
Yeah, go ahead. Sorry, finish. Aditya? Can anyone else hear him?
No. No, Alpan, I cannot. Do you
Yeah,
want
no,
to just answer to the Parth question, at least, that you've understood? Would you like?
Yeah, I would. I'm just hoping that Aditya is online. He may have lost internet.
yeah, I'm back. Sorry,
Okay,
I don't
okay.
know what happened.
Yeah.
I don't know where I got off.
Yes, you were
Yeah,
mentioning
so I hope you.
two approaches. One is
Yeah,
to
did you get the
restrict
second?
yeah, the second was looking at public data for a certain domain and exhaustively looking at all the public data that's available. Right?
Yeah, and then it will emerge whether there's potential for AI to solve that problem,
Yeah,
or not,
yeah.
or any problem in that domain.
Yeah, so let me address both. So I think regarding the first, we may end up doing it again, like to hear Shekhar's opinion on this, but my view is that we may end up doing that in the long term. But I think it's too early for us to hone in on a class of solutions, especially when we are still not clear about, what will stick, what will be deployable, where will we get, what types of solutions will we get partners for, who will help us deploy and scale. We still haven't carried out a single solution that is deployed to scale, right? So it's a bit premature to then sort of restrict our space and say that, this is the space that we are going to focus on. I think that's sort of setting ourselves up for failure in some ways. That is one. To your second question, I think what we found in many cases is that public data is fairly useless. I mean, it's good for doing Kaggle type competitions and doing Kaggle types analysis, but it often doesn't result in deployable models. So I don't think we'll be able to run away from primary data collection or accessing proprietary data that's not available to all. So that's my take on it.
And Alpan is correct on both. In fact, totally correct on both. The only thing I will add is on the first point. It's at the stage at which we are. There's a couple of things that will emerge over a period of time, and that will have to emerge through our experience. It cannot be postulated, or it cannot be articulated in our mind. It has to come through experience. So two things will happen over time. One is we will find one or two very good sweet spots. And the moment we find that, we really want to go after that very hard, because if we get a good sweet spot, then we want it to be replicable across. A small example again is IDSP equivalent, the ability to look at text, this, that, and the other. It's a small example, but the other piece, which is very important to understand, is in a world or in an environment where decisions are made in a very haphazard and random manner today, the ability for AI to even slightly outperform. It's like the story they say, if there are two guys and there's a bear running after them, they need not run faster than the bear. The person X needs to run faster than the person Y. It's the same thing. In other words, we don't need to be dramatically brilliant in AI yet. You just have to be better, systematically better than what is offered on the ground today. And when you do that, it allows a little bit of it's a little bit difficult sometimes to explain to counterparty. But the fact is, if today is so random, when you systemize it, it's better than random. And that's really how you get into AI adoption at the beginning. And over a period of time only, we will understand where we will go. We will not understand it today. We are still at least 1, if not 2 years away from formulating our thought process with clarity. And the second point, Alpan is dead on. To try and boil the ocean in order to find a needle will not work. Because most of the ocean is irrelevant. All the data is irrelevant. All the information quality is poor. Most of it doesn't make sense. We really have to rifle shot and get to our data collection and related exercises with a clear problem definition. That's all.
Yeah. Plus, I would just add that most of public data is aggregate data. It's not data of individuals. And most of our solutions operate on individuals.
Okay, thank you.
Okay, we have 7 minutes. I can either go on and I think maybe I should just go on. So yes, the whole process of annotation, which we've already discussed in the past. And so a lot of this will also be recap because we've discussed it through questions that people have asked. So we prematurely discussed a lot of this. So as we all know, annotation is the process of assigning a label to data. And sometimes the label itself is part of the data collection effort, as in, for example, Nikshay labels that we have in Nikshay, or, when we do cuff sounds for our TB, TB screening project, we are going to also test whether the individual has TBM. Right? So it's part of the data collection effort. In other cases, it's not. So in pest management, for example, we have a separate process where annotators actually put bounding boxes around the pest so that they can be counted. Right? So it's a separate effort. And the AI algorithm, as we know, learns the mapping between the features and the annotated label. And for new data, it is then learned to predict the label. Now, when you verify this predicted label through human annotation, that is called evaluation. This is really, in the simplest terms, this is what we mean by evaluation. Forget about math, forget about metrics. Fundamentally, it's this process of verifying whether the AI predicted the right label. And who verifies this? It's always a human. So we are assuming that the human is right and the AI is wrong. So, or AI could be right or wrong. Right? So this is a very important assumption. And this leads us into various problems, as we'll see. But this is the only thing we have to fall back on. The human can be an expert, but it is a human. Examples are the person has or does not have the disease, where a human does a test to check if the person has the disease. Bounding boxes, as I've already mentioned, judging whether an image is of good quality or poor quality. There could be an AI model that does this, a human that verifies this, right? Some types of annotation are required for internal algorithmic development purposes. And in such cases, the annotation is not the label that we try to predict. And one example is the key point annotation in the Anthro project. I'm not going to go into the technical details there, but it's sort of a subsidiary annotation that actually helps the AI algorithm in predicting the weight. So when it's
Alpan,
difficult to do, yes,
Alpan, I think just to clarify, is key point annotation where somebody just takes a baby and marks the hand, the elbow point, the palm, the leg,
exactly.
and stuff like that. That's like the key points of a baby is all.
That's the key
and
points
that's
of
kind of That's a training wheels, if you will, for the AI to kind of assist it in its process in the beginning.
In the beginning, it's training wheels, but also what we found is if the AI simultaneously tries to predict both the key points and the weight, so it can be used as an auxiliary label. If it simultaneously tries to predict both, then the weight accuracy performance also improves.
So that's very interesting. So you may have some subsidiary efforts which actually
Yes,
over a period of time just causes by the very way AI is designed or
yes,
you design your algorithm, it will cause an improvement.
that's right. That's
And
right.
what happens, Alpan, this is, I think, super important for us to understand that what you said, human is always right and AI may or may not be right.
Yes,
Therefore, huge attention needs to be paid in cases where you can have subjective judgment on any matter. No, you need to suppose you read an
exactly.
article and we are supposed to say is it good or bad. You may agree it's good, I may agree it's bad, etc.
Yes,
So
and then there
what
are
you do?
various ways of dealing with subjective annotation. So, uh, I mean, even in a sense, even this bounding box, object detection is subjective because different humans can draw a bounding box around an object in different ways,
So
and they
what
can
do
all
you
be
do?
right.
So
So
how do
then you
you?
have to deal with consensus. You have to do a label averaging across human annotators, things like that. It can
All that.
also be incorporated into the AI modeling process where your loss functions. I'm sort of going ahead of myself here. Your loss functions can take into account agreement with individual labelers separately. And
Okay. So, but it's very important to address all this explicitly. No?
yes, yes, correct, correct. So I mean, there's objective annotation. I haven't gone into this actually here, but there's this, annotation has become a fairly nuanced field, and there's this idea of objective versus subjective annotations, like what you mentioned. There's this idea of simple versus complex annotations. So simple annotations are simply a class or a number, whereas objects are complex annotations. If you're predicting ranks, that's a complex annotation, for example. Complex annotation tasks are very tricky. Um,
So this
and
also could be a determinant of problem selection because
this is also
there is
determinative.
there
Yes.
is an expectation that there is a level of agreement expertise in order to reach a conclusion because as far as the AI is concerned, aside from some incursions it makes into the algorithm, the human decision is it. That is it. That is super important then.
Yes, yes. And therefore, I mean, so while we understand that high quality annotation is an essential component of high quality training data, it's often true that doing high quality annotation is difficult. And that's where human experts come in for annotation. And so it's often the case, especially in the kinds of problems that we look at, it's often useful to create a gold standard data set that is annotated well by experts. Now, when you create a gold standard data set, by definition, it's being annotated by experts. And we've seen this in the LPA project. It took a lot of time to create a gold standard data set because there was one expert doing all the annotations. And we didn't trust anybody, at least the CTD didn't trust anybody else to do it. So what happens in situations like this? Typically, these gold standard data sets, which are very well annotated, are small data sets. And they should never ever be used in training models. Because in a sense, the AI should, the gold standard data set should only be used for evaluation. If you use it in training, you have nothing left to do evaluation on. Your evaluation always has to be against a gold standard data set, the most accurate data set you can find, because then that is what will reliably tell you whether your model is working well or not.
And Alpan, the reason, I mean, it's kind of slightly counterintuitive for some of us. I think the reason is because in the real world, you cannot afford to have that gold data set. So in the real world, you'll get a whole boatload of, things. And in the real world thing, otherwise, why would it not be that you just go ahead and train the model on the gold data set and it should perform very well everywhere else?
Two reasons. One is the gold data sets are usually too small to train on. So they're not good for training. That is one reason. The second is you want an objective judgment of the performance of the model. And that only a gold data set can give you. If you use it up in training, you will never get that objective judgment. Now, of course, both of these break down if you have the ability to create a large gold standard data set and create them at will. But usually that's not the case. So I'm at time, so maybe I think I should stop here. And we'll continue in the next session.
Yes, Alpan. I think so.
Thank you, Alvin.
Any questions before we sign off? Okay, there's a lot to sink in. I'll share this as usual on the Slack channel, and we'll continue from this point next time on Friday.
Thanks, Alpan.
Thank you.